Hello students, in this lesson we're going to learn about transformations of graphs. So we're going to look at various basic functions and their graphs. You're going to need to memorize this, and then we're going to learn how to transform them, which means sliding them around in the plane, sliding them around on the graph. So we'll begin by talking about our identity function and our constant function. These are both linear functions. They're both going to be straight lines. The identity function is that function whose graph will cut quadrants 1 and quadrants 3 perfectly in half. This is called y equaling x. This is the identity function. When you draw the identity function and you draw it perfectly, this would be a 45-degree angle. So it would have a slope of 1, and that's your identity function. Now, I write y equaling x, but since it passes the vertical line test, it could have been rewritten in the true function notation f of x equaling x. Now the constant function is really any horizontal line. Okay? And any horizontal line will be y equaling a number like y equaling 2, y equaling 3, y equaling 5. If you have a horizontal line, it again is a linear function. It is referred to as a constant function. And so it is also listed. Now your vertical line is not a function, and that's why it's not included here. Now let's take a look at a bunch of different functions and their basic graphs. The quadratic functions are y equaling x squared, or we could have put it in function notation because it is going to pass the vertical line test. It is called a parabola, and it will look like this. It is a U-shaped graph. Okay? So that is what your y equaling x squared basic function looks like. It will have a vertex at the origin. Your next one is your cubic function, y equaling x cubed, or in function notation because it does pass the vertical line test, f of x equaling x cubed. And its general graph will look like this. It will be increasing, and then it will kind of swing through or squiggle through the origin. It does pass through the origin. The next graph is the square root function. Again, it is a function. It will pass the vertical line test, so we can write it in function notation. It begins at the origin, and then it will be always increasing, but it kind of levels off. It is never going to be absolutely horizontal. It will never be a constant function. It's just it doesn't rise very quickly. Our cube root. Now the cube root, this is called the index. This little number on the hook is called the index. It's assumed to be 2 in the square root function, and a 3 in the cube root function, and a 4 in the fourth root. But again, it is a function. We could write it in function notation, and it looks like this. Now it looks a little different. It looks like this. Okay, not to be confused with x cubed because it's a little flatter. Again, it is never constant. It is never perfectly horizontal. And this is your cube root function. Your absolute value function, again, I could write it in function notation. It is our V-shaped graph. Okay? That's what your absolute value function looks like. And it, too, is going through the origin. Now, the reciprocal function is a little bit odd. It has what we call asymptotes. The y-axis is one asymptote, and the x-axis is the other asymptote. Now, we will talk about this at length later in the semester, but it looks like this. In other words, it will always approach, drawing closer and closer to the asymptotes, but it will never cross or touch them. So those are your basic functions. You need to kind of memorize these because you're going to be moving them around in the plane. So these basic functions, you need to have in your mind a vision of what each of these looks like and what their equation is. Now, the first transformations we're going to do are shrinking and stretching them vertically. It's kind of hard for me to say it's vertically shrinking. Sometimes I will use the word compressing. Now we'll start with y equaling x squared, as our what we call parent function or a base function, and then we will stretch it. So if we want to begin by looking at a basic table of the values to graph this, we're just going to use some pretty simple x values, 0, 1, and 2. 0 squared is 0, 1 squared is 1, 2 squared is 4. Let's go one more. If x is 3, x squared is 9. So to graph the original function on the graph paper, we're going through the origin, 1, 1, 2, 4, 3, 9, and it will grow from there. And actually it is a U shape, so when you reflect these values over, you will get the full image of your U shape. Now this does not come down to a point. It's curved at the bottom around the origin. There's our original y equaling x squared. Now I'm going to change my pen color, and I'm going to go into orange, and I'm going to transform this graph, and I'm going to now multiply it times 3. So it's y equaling 3x squared. Now if I'm going to do 3x squared and I want to graph it, what it's going to do is it's going to be a U shape still, but it's going to be a little more narrow. So if you really want to see the values, I'm going to draw another column in this table, and since, let me change this up just a little bit, this would be your x squared values, and now we're going to have our 3x squared values. So if you take this column, if you take the x squared column, this column of values here, which for 3x squared, you would just multiply every number in this column times 3. So that's what we will do. 3 times 0 is still 0. Sure, I'll put this right. Okay. 3 times 0 is still 0. 3 times 1 is 3. 3 times 4 is 12. And 3 times 9 is 27. So these ordered pairs for this y equaling 3x squared graph, on here we still go through the origin, but at 1 we will be up at 3. At 2 we will be way up here already at 12, kind of off the charts. And also on the opposite side of the y-axis, this is a little harder for me to graph sketching it on a tablet, but this is what your y equaling 3x squared looks like. So it's still a U-shaped, but it's more narrow. So it has a vertical stretch on it, a vertical up and down stretch on it, which is causing it to look more narrow. Now if I do another type of vertical transformation, instead of doing something like 3, I might do something like 1/4 x squared. Okay, if I do 1/4 x squared, it will be 1/4 of all of the x squared values in the yellow column. So 1/4 of 0 is 0, 1/4 of 1 is 1/4, 1/4 of 4 is 1, and 1/4 of 9 is 9/4, which is 2 1/4. So let's try to graph those points. So we still have the origin 0, 0, but at 1 we're only at 1/4. And at 2 we're at 1. And at 3 we're at 2.5. So what's happening here is the graph is wider, a little flatter and wider. It is still a U shape, but when you multiply it times a fraction, it gives it what's called a vertical compression or a vertical shrinking sensation to the graph, and so it will be kind of flatter and wider. So this is your y equaling your 1/4 x squared. So we can conclude if you multiply it times a fraction, this is called a vertical shrink or a vertical compression, which makes it flatter. It does not rise as quickly. If you multiply it times a number bigger than 1, like 3, it is considered a vertical stretch. So you have a vertical stretch and a vertical shrink. So if I multiplied it by 3, it would be stretched. If I multiplied it by 5, it would be stretched. If I multiplied it by 10, it would be stretched. For it to shrink, I would multiply it by a fraction, like a half, a third, a fourth, or 2/3. So to summarize this, let me go back to my black pen. If we summarize this, now the book summarizes this in a little bit of different notation than we're used to, so let me explain something. If we say y equals x squared, we also could call this y equaling f of x, because f of x is our x squared. So we could recall this f of x. So if I come in here and I multiply it times a number like 3, so I have 3x squared, this would look like 3 times f of x. Or if I come in here and I multiply it times 1/4, it could also be rewritten as 1/4 f of x. So in summary, in the textbook, when it says something like a times f of x, this statement here, if a is greater than 1, meaning if a is 3, or if a is 5, or a is 10, then that's going to be a vertical stretch. So you have a vertical stretch when a is greater than 1, when the number in front is greater than 1. Now if I want to have a fraction, that would mean a was less than 1, right? A half, a third, a fourth. But we want it to still be a positive fraction, so we put it between 0 and 1. So if we multiply times a fraction, this is where we get the vertical compression, which opens up the graph or flattens it out. Okay, this is also referred to as a vertical shrink. So that's kind of your summary and your pattern of doing vertical stretching and vertical shrinking or compressing. Okay, the graph is really your strongest probably visual on understanding this. Alright, so now let's go to another one and do some of this vertical shrinking and vertical stretching. Alright, so suppose I take this function, I'm going to just leave it as is first, and I'm just going to graph absolute value of x. Well, let's get a table of values so we know what this looks like. 0, absolute value of 0 is 0. 1, absolute value of 1 is 1. 2, absolute value of 2 is 2. And we can go negative. Absolute value of negative 1 is 1. Absolute value of negative 2 is 2. Now if you graph these points, 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2, this is where you get your V shape. Okay. So that is your parent function, your f of x equaling the absolute value of x. Now if I want to give it a vertical stretch, I'll put a number in front of that absolute value. Like suppose I take 3 times the absolute value of x. That's going to give me a vertical stretch because I'm multiplying times a number bigger than 1. A vertical stretch. So what that's going to do is it's going to multiply all these y values in this column. It's going to multiply all of these y values times 3. So 0 times, I'll put 3 absolute value of x. 0 times 3 is 0, 1 times 3 is 3, 2 times 3 is 6, 1 times 3 is 3, and 2 times 3 is 6. So when I graph this y equaling 3 times absolute value of x, I'm still going through the origin, but I'm going through 1, 3, 2, 6, and negative 1, 3, to negative 2, 6. And so you can see it has a vertical stretch, meaning it's climbing faster because I multiplied the function times 3, a number bigger than 1. Now let's do a vertical shrink, and I'll go back to green, and let's try a fraction in front of the absolute value, like maybe 1/2 times the absolute value of x. It's a fraction. So this is supposed to be a vertical compression or a vertical shrink, which is going to flatten it out. Alright, so let's build another column over here in green, and let's let this column be 1/2 the absolute value of x. Okay, 1/2 times the numbers in yellow. 1/2 of 0 is 0, 1/2 of 1 is 1/2, 1/2 of 2 is 1, 1/2 of 1 is a half, and 1/2 of 2 is 1. So I'm using my x's and my 1/2 absolute value of x to graph. So I'm looking at 0, 0, still the origin, 1, 1/2, 2, 1, negative 1/2, and negative 2, 1. So these are kind of hard to see, but my green graph is flattened out a little bit. It is a vertical shrink because I multiply times a number less than 1. Okay, so now let's take a look at what comes up next. I'm going to clean this up just a little bit. Okay, so here we go now. Let's see what's next. Now that was vertical stretching and shrinking, and that's what we normally do. The horizontal stretching and shrinking, we actually don't do this very much, and you will not be tested on this, but I want to at least show it to you. When you horizontally alter something, then you need to be altering the x. Okay, you need to alter or change the x variable. Okay, doing something to the x if it's horizontal change. So in other words, if I have a function 3x squared plus 4x and I want to make a horizontal transformation to it, then I would change x by doing something like replacing it with a half x. So if I came in here and I replaced every x with 1/2 x, that would give me a horizontal transformation. So this would end up being 3 times 1/4 x squared plus 4/2 x, which is 2x. So this would ultimately be 3/4 x squared plus 2x. Now it's hard to see a horizontal transformation. You can graph this on your calculator and take a look at it, but it's going to be just the opposite of what you expect in the graph. So if you take x and you multiply it by a number less than 1, you multiply it by a fraction, this is actually a horizontal stretch, the opposite of what you would expect. Pretty much all horizontal changes are going to be something opposite of what you anticipate them being or what would seem logical. Now if I wanted to do a horizontal shrink, then I would use a number instead of 1/2 x, I would use something like 5x, multiply times something bigger than 1. So this would be 3 times 5x being squared plus 4 times 5x, or 3 times 25x squared plus 20x, which ends up being 75x squared plus 20x. So this turns out to be, even though you're having bigger results, this turns out to be a horizontal shrink. Now again, this is not something that we're going to put a lot of focus on. I just wanted to show it to you. So in summary, if you take f times a of x and you pick a to be if a is a fraction, meaning if a, well let me check, if a is a fraction, meaning a is less than 1, but we also want to be positive, so we have to put it between 0 and 1. If a is a fraction between 0 and 1, this is actually a horizontal stretch. If a is bigger than 1, like in the 5 above, this is opposite of what you would expect. It is a horizontal shrink. or horizontal compression. Okay, so let's move on. Let's take a look at translations. Now these are going to be taking the graph, kind of the rigid graph, and sliding it left and right or up and down in the plane. So we can slide left or right. So take, for instance, back to y equaling x squared, and I'm just going to quickly sketch, a U-shaped graph. It's not going to be, technically correct. I'm just going to throw it on the graph. Now, if I want to make a slide to this graph, then I need to change the x. So if I come in here and I do something like put x plus 3 before it's squared, a number grouped with x, this is going to move it either right or left. And strangely enough, this is going to be left 3 units. So now, if I make this translation by going left 3 units, and I wish I'd done this in a different color. Okay, so what I'll do is I'll just come in here and I'll put an arrow in orange. If I'm going to take it left 3 units, then this origin is going to go left 1, 2, 3, and this graph will look like this. Just shift it to the left. So the orange graph is y equaling x plus 3 squared. Now if I want the graph to go to the right instead of to the left, oddly enough, I would put a minus sign in here. If I put a minus sign in here, strangely enough, opposite of what you think, it's going to go right 2 units. So the black original U shape at the origin is my original graph, and this one would take it to the right 2 units. It would look something more like this. Okay, so the shifting might seem a little strange, opposite of what you expect, but that is how it works. So there's my left and right translations. So remember, your horizontal movement left and right is opposite of what you think it should be. So when you come down here to the summary, when you add a constant, oddly enough, this is left C units. But if you subtract, this is right C units. Okay, so now let's practice on another one. Suppose we use the square root of x, and we know that square root of x starts at the origin. It looks something like this. So now if I want to alter it horizontally, if I want to come in here and I want to move it, say if I choose, I want to move it left 5, then that would be x plus 5. That would be left 5 units. So if I moved it to the left 5, it would be over here 1, 2, 3, 4, 5. Be the exact same rigid graph, slide it to the left, and it would look like that. Now if I want it to go right, then I would have to take and subtract something. Maybe I want to go right 3, then I'd put x minus 3. That would be right 3 units. So I would take the original parent function, which is just the square root of x, which is the black line starting at the origin, and I would go right 3 units and replicate the graph. Those are your left and right translations. Now I can also slide my graphs up and down. So suppose I start with the parent function, which is y equaling x squared. Again, I'm just going to rough draft a U-shaped parabola. And if I want to go up or down, then how to make that occur would be on the outside to the right of the equation. If I were to put x squared plus 5, that would be up 5 units. So my origin would go up to the 5. It would be the exact same graph, rigids, exactly the same, up 5 units. If I want the graph to go down, I could do something like y equaling x squared minus 4, and that would be down 4 units. So the original y equaling x squared in black ink would go down 4 units, and the graph would look like this. So the up-down movement is on the outer edge of the function. So in the summary, when you look at this, when you add a constant to the end, you go up that many units, and when you subtract, you go down that many units. Okay, let's get some combined examples in here and see if we have this figured out. This is a function. It's your parent function, your start function is y equaling x squared. So, like I said, this is not accurate. I'm just sketching a U shape. Now, if I come in here and I put x plus 3, I group the 3 with the x. That's horizontal change. If horizontal change is opposite than you expect, this is going to be left 3 units. So if I take this left 3 units, the origin is going to move to the negative 3, and it's going to look something like this. That is my graph moved to the left 3 units. Now, if I put the plus 5 on the end, and I'm going to change the pen color. Now if I come in here and I put plus 3 squared plus 5, the plus 5 on the end is up 5. So this graph up 1, 2, 3, 4, 5, here is the final graph in blue. Now notice the origin here. I started at the origin, not the origin of the vertex. I started at the origin. When I moved it left 3 and up 5, the vertex of this graph is now negative 3, positive 5. Let's do another one. Okay, this is an absolute value of x function. One of the things that's happening here when it is the minus 4. When you're collected with x, as this is, your opposite is what you think it's supposed to be. This will be right 4. Okay, your absolute value of x is a V shape. And I'm going to do, that's not a very good one, but I'm going to go left 4 over to this location. Oops, I'm sorry, not left 4. I'm going to go right 4. I think I'll go ahead and change the pen color. I'm going to go right 4 over here with my V shape. Okay. Then if I come in here and I put a 2 in front of it, the 2 in the front is my vertical stretching or compressing. Since 2 is bigger than 1, this is a vertical stretch. It's going to make it more narrow. So when I make it more narrow, it's going to look, like I said, I'm just going to do a sketch. It's going to narrow it up like that in green. Then if I come in here, I guess I should have written that down. This is a vertical stretch. Then if I come in here, and on the end, on the outside, I add 3, this is up 3 units. I'll do this one in blue. So the green is going to go up 1, 2, 3 units, and this will be my final graph in blue. Now, in blue, let's think about the origin, the vertex, where the origin was translated to. The origin was translated to the right 4 and up 3, so this has a vertex of 4, 3. That's your final graph. What a mess, but that's your final graph. Okay, here's another one. This one is starting your parent function of y equaling x cubed. Our x cubed graph looks something like this. Whoa! I got carried away. I don't know why I keep getting it curved more on the end. That's your x cubed graph. So then when we come in here and we take x minus 2 cubed, this is the minus 2 is collected with x, it's opposite of what you think. It will be right 2 units. So this origin is moving over here to the right 2. I'll convert it to orange. So now it's going to look something like this. Okay, my next step is to put a 3 in the front. The 3 in the front is my vertical transformation. Since the 3 is bigger than 1, this is a vertical stretch. Again, I'm just doing a sketch, just kind of a rough sketch of this. So if it's stretched, it's going to kind of narrow it up a little more. Let's say about like that. And then my last step, this is very messy, but the -4 on the end is where you go down 4. So I take that green line and I take it down 4 units. 1, 2, 3, 4. And it should look something like this in blue. That would be your final graph. It's not very good. Let me try it one more time. There it is in blue. That would be your final graph with all of the transformations in it. Okay, so now there's another one, alright? So this one would start with y equaling the square root of x. Then, when you put the x minus 5 in here, and I'll put parentheses, I don't have to, but I tend to do that naturally. Horizontal movement is the opposite of what you think. It should be, it will be right 5 over here. When you put the 1/2 in front, this is going to be your vertical transformation, which means you're going to give it a vertical, since it's less than 1, it's a vertical shrink. So this would be, I'm going to go ahead and put it in green. It's going to flatten it out a little bit like that. Then when you come in here and you put +4 on the end, that is up 4 units. So the green line up 4 units. 1, 2, 3, 4. Flatten out a little bit. Looks like that. Your final graph is in blue. And this point, after it started at the origin, it moved right 5 and up 4. So this is the point 5, 4. Okay, this is our rational graph. This is the one that had all the asymptotes. So you start with y equaling 1 over x, which looks like this. Then when you change it, remember this -2 is along with the x, so this is horizontal change, opposite the direction of what you think. It's going to be right 2. Now when I move it right 2, and I know this is kind of hard to understand, and we'll get into this in greater depth later in the semester, it's going to look like this. Then when I come in here and I add 3 on the end, this is going to take it up 3 units, which I will close the blue. I go up 3 units, it will be up here like this. In blue. I wish I could erase some of these lines. Let's see if I can get rid of some of them. Yeah. This would be your final graph. Okay, so before I move into reflections, this is a rather long recording. I think I will stop this recording and then start a new one.